Hi students, welcome to Sunil's tutorial. I'm Sunil Milwani and today we'll be doing this chapter called as gravitation. Let's see this. Let's find out the weightless condition of an astronaut in an orbit. In orbit. Now, let's consider this. First, let's understand the meaning of weight. When an astronaut of mass m is on the surface of the Earth, his weight is mg. On surface of Earth, his weight is going to be equal to mg. That means he exerts a force equal to mg on the ground. So if this is your astronaut, he is going to exert a force of mg on the ground. Now if he exerts a force of mg on the ground will also exert an equal and opposite force of reaction on the astronaut. Due to this, so the ground is going to exert a reaction force. This is my normal reaction force that will be exerted by the ground onto the astronaut, and owing to which this, as the ground exerts an equal and opposite force of reaction on the astronaut, due to this force of reaction, the astronaut has a feeling of weight when he is on the surface of the Earth. Right? Do we get this thing here? His weight is mg. He exerts a force equal to his weight on the ground. The ground also exerts equal and opposite force of reaction on the astronaut, and due to this reaction force he has a feeling of weight. Due to this reaction force he has a feeling of weight. Fine, do we get this in here? Now, when the astronaut is revolving in a satellite round the Earth, both the astronaut as well as satellite have the same acceleration towards the center of the Earth. Due to this, the astronaut cannot exert any force on the floor of the satellite. As a result, the floor of the satellite also does not exert any reaction force on the astronaut, and it is due to this lack of reaction force that the astronaut inside the orbiting satellite has a feeling of weightlessness. Do you understand? When he is on a satellite, the satellite and the astronaut have the same acceleration towards the center of the Earth. In a satellite, both the astronaut and satellite have the same acceleration towards the center of the Earth. Right? Due to this, the astronaut cannot exert any force on the floor of the satellite. Due to this, the astronaut cannot exert any force on the floor of the satellite. Right? As a result, the floor of the satellite cannot exert any reaction force on the astronaut. The floor of satellite cannot exert reaction force on the astronaut, right? And due to this lack of reaction force, there is that feeling of weightlessness. Due to lack of reaction force, there is a feeling of weightlessness. Right? So do we understand why astronauts feel weightless on the inner satellite? Now let's try to mathematically prove this. Let us assume that a satellite of mass m is revolving around the Earth with an orbital velocity v in a orbit of radius r. A satellite, consider a satellite of mass m revolving with a speed of v in orbit r, right? In that case, since the satellite is revolving in the orbit, the centripetal force is going to be generated by the gravitational force. I can say that centripetal force should be equal to the gravitational force, right? Centripetal force we know is nothing but, here it is going to be mv square by r. Gravitational force is going to be nothing but gmm upon r square. So r and square gets cancelled, in which case you will get v square. Now let's not cancel that r. In that case I can therefore say m and m gets cancelled. I can say v square by r is gm upon r square, right? Now let the astronaut have a mass of m bar inside the satellite. Mass of astronaut, let us assume, is equal to m bar, right? Now he is acted upon by the forces of gravitation, right? He is acted upon by two forces. He is acted upon by two forces. One is the gravitational force, which is nothing but g m bar upon r square, and the reaction force, r of the base of the satellite, in opposite directions, right? In that case, the net force acting on the astronaut is going to be the net force, therefore net force acting on the astronaut is going to be gmm bar upon r square minus the normal reaction force, right? Now this is going to be, this is going to be directed towards the center because it's a centripetal force, directed towards the center, right? Now in that case, since he is moving with the satellite, I can say that gmm bar upon r square minus r should be the centripetal force, that is m bar v square by r. But here I could say that divide by m bar. If I divide by m bar, I get gm upon r square minus r upon m bar is equal to v square by r. I'm dividing by m bar. Now once you have this, I can substitute the value of v square by r. We found out that v square by r is gm upon r square. So I'll get gm upon r square minus r upon m bar is equal to gm upon r square. So gm upon r square minus gm upon r square is r upon m bar. 0 is r upon m bar, therefore r is 0. As the net reaction force is 0, therefore the astronaut has a feeling of weightlessness. Right? This is the reason why, this is the theoretical aspect of it, and this is how you practically prove that the astronaut will feel weightless on a satellite. Now let us try to find out the variation of G. Variation of G due to altitude. Let's consider a body of mass m is placed on the surface of the earth where the gravitational acceleration is g. Consider a body of mass m placed on surface of earth where gravitation is say g, right? In that case, the weight of the body will be equal to mg, right? And the weight of the body is equal to the gravitational force acting on the body. Weight is equal to the gravitational force acting on the body. In which case you could say that okay, now if m is the mass of the earth and r is the radius of the earth, then the gravitational force acting on the body, if m and r are mass and radius of earth, then gravitational force acting on the body is going to be nothing but gmm upon r square. That means I can therefore say that mg, both are gravitational force, therefore I can say that mg is equal to gmm upon r square. M and m gets cancelled, so you will get g is equal to gm upon r square. Now, if the body is taken to a height h above the surface of the earth, if the body is taken to height h above the surface of the earth, in that case I'll get mgh, that's the weight at height h, should be equal to gmm upon r plus h the whole square. That's the gravitational force at that height. So I can say m and m gets cancelled, so you will get gh is equal to gm upon r plus h the whole square. Now divide the two equations. In that case I'll get gh dividing equation 1 and 2. We'll call this as equation 2 and we will call this as your equation 1, right? So if I divide equation 1 and 2, I will get gh upon g is gm upon r plus h the whole square upon gm upon r square. So in that case I'll get gh upon g is r square upon r plus h the whole square, right? In that case I can say that numerator can be written as denominator of denominator. So that is 1 upon r plus h the whole square upon r square. I'm writing the numerator as denominator of denominator. Gh upon g is 1 upon r plus h upon r the whole square. Gh upon g is 1 upon 1 plus h by r the whole square, right? Now, once you have this, if I take this in the numerator, I will get gh upon g is 1 plus h by r raised to minus 2. Now, I can expand this by using binomial theorem. Expanding using binomial theorem. If I expand using binomial theorem, all the terms other than 1 plus h by r raised to minus 2 will approximately be equal to 1 minus 2h by r, because all the other terms which are of higher order of h will become 0. So in that case, therefore I can say that gh upon g is 1 minus 2h by r, right? In that case, therefore I can say that gh is g 1 minus 2h by r. This is how the gravitational force changes with altitude, right? So gravitational force at height h is gravitational force on the surface of the earth 1 minus 2h by r. Can we get this in here? Next, let us consider the variation of g with the shape of the earth. We did variation of g due to altitude. Let's consider variation of g due to shape of earth, right? In which case I can say that measurement of g at different places on the surface of the earth has proved that earth is not a perfect sphere, right? It is in the form of an ellipsoid, wherein it's bulging at the equator and it is flattened at the pole. Now, this particular shape of the earth is due to, it is believed it is called due to the rotation of the earth. Now, we know that g is equal to gm upon r square. Therefore, I can say that g is inversely proportional to r square, because the universal gravitational constant and the mass of the earth are constant. Thus, the value of g at a place varies inversely as the square of the radius of the earth at that particular place, right? Now, as the value of radius is greatest at the equator, therefore g is least at the equator. Guys, see this. This is the equator. Radius of the equator is going to be maximum, and we said that g is inversely proportional to radius. So since the radius of the equator is maximum, therefore the value of g will be minimum at the equator, and since the radius of the poles is minimum, therefore the value of g will be maximum at the poles. Fine, do we get this thing here? So this is how the value of g varies with the shape. Since it is bulging at the equator, the radius is maximum at the equator, therefore g is minimum at the equator. It is flattened at the poles, therefore the value of g is least at the poles. The value of r is least at the poles, therefore g is maximum at the poles. Next, let us find out the next thing. Let us find out the variation in g due to the rotational motion of the earth. Variation in g due to rotational motion of earth, right? Let's see this. Equator. Let us consider a particular latitude. This is at an angle of theta. Let's assume r is the radius of the earth, right? And the radius of this particular latitude, let's assume, is small r, right? Now, let's consider this point as P. Now, what are the forces that are going to be acting at this point? The force, let's consider this. We want to find out the value of G due to the rotation motion of the earth, right? Now, let us consider a particle P of mass m situated. Consider a particle P of mass m situated at point P at a latitude of theta. Right? Now, as the earth rotates about its polar axis, the particle P will revolve in a circle of radius r. Particle P revolves in a circle of radius r, right? Now, with an angular velocity of say omega, it is revolving with an angular velocity of omega. In that case, the particle is subjected to a centrifugal force. The centrifugal force acting on the particle is going to be F, which is going to be mr omega square. That is going to be the force that is going to be directed radially outwards. Guys, see in the diagram. This is that force mr omega square, which is going to be directed radially outwards, right? Now, the component of this force F along the radius OP of the earth, if I resolve this along this radius, it will be mr omega square cos theta. That will be the component of this force along the radius. So, component of this force along radius will be mr omega square cos theta, right? Once you have this, then I can say, let us assume that g is the value of acceleration due to gravity in the absence of rotation. Let's assume g is gravity in absence of rotation. Then the force of attraction exerted by the earth on the body is going to be directed towards the center of the earth, is going to be mg. Force of attraction directed towards center is going to be mg, right? Now, due to the rotation of the earth, a force mr omega square cos theta acts radially outwards. Therefore, the net force that will act on the body, see, guys, can you see the diagram? A body here, weight mg is going to act in inward direction, right? And I have, due to the rotation, I have a force mr omega square cos theta acting in outward direction. So what will be the net force acting at this point? It will be nothing but the difference between the two forces. So I can therefore say, see, due to rotation, mr omega square cos theta acts outwards. Therefore, the net force of attraction exerted by the earth is going to be, say, let's call that as mg bar, which will be nothing but mg minus mr omega square cos theta. Mg is the force that is directed radially inwards. Mr omega square cos theta is the force that is acted radially outwards. M is common, I can cancel. So G bar is equal to G minus R omega square cos theta. Right? But I can say that if I apply you could say that from the figure, what's the relationship between R and R? I can say R is equal to R cos theta. Guys, look at this. Can you please see this, guys? Radius. Right? So I can say that cos theta, guys, if I were to drop a perpendicular here, cos theta would be nothing but R upon R. Therefore, I can say that R is equal to R cos theta. Right? So once I have this value, I can substitute the value of R, in which case I will get G bar is equal to G minus R cos theta omega square cos theta. So in that case you will get that G bar is equal to G minus R omega square cos square theta. Right? This is how the value of G varies with the latitude theta. This is the variation of G due to latitude theta. Let's consider if this works. Consider case 1. Case 1 at latitude theta is equal to 0 degree. Cos of 0 is 1. Therefore, I can say that G bar is G minus R omega square cos of 0. So, at the equator, this is going to be my value of G. Right? You are subtracting the entire R omega square. This is minimum value of G. Right? Let's consider at the poles. Case 2. At poles. At the poles, theta is 90 degree. So G bar is equal to G minus R omega square cos 90. Cos of 90 is 0. So G bar is equal to G, which is going to be my maximum value of G. This is max value of G. Right? So as I move from equator to the poles, the value of G goes on increasing. Next, let us see variation in G due to depth. Variation in G due to depth. Now, we already know that G is equal to Gm upon R square, right? That is on the surface of the earth. Surface of earth, where M is mass of earth, and R is radius of earth. Right? Now I can say that if rho is the density of earth, rho is density of earth, then in that case I can say that mass is density into volume. Density is rho. For practical purposes, we'll assume that the earth is spherical in shape, so its volume will be 4 by 3 pi r cube. Right? So in that case you will get, now if I substitute this value of mass in my equation, I will get G is equal to G m. Instead of m I can say rho into 4 by 3 pi r cube upon r square. So in that case I will get G is equal to G rho 4 by 3 pi r which can be written as G is equal to 4 by 3 pi G rho R. Right? Now, let us consider, this is my gravitation force on the surface of the earth. Let us consider a point P which is at a depth of D from the surface of the earth. This was on the surface of the earth. Let's go beneath the surface of the earth. This is at a depth of say D, right? This radius we know as R. So this radius will be R minus D, right? So we will say consider a point P. Consider a point P at a depth D below the surface of the earth. Right? In which case I can say that, if I use the same analogy, I can say that mass of the inner earth density will remain the same, volume 4 by 3 pi r cube, but now the radius of the inner earth is going to be r minus d, so this is going to be 4 by 3 pi r minus d the whole cube, right? Similarly, the gravitational force on the inner earth, that is on the smaller sphere, we'll assume that as g bar. So g bar will be gm upon r minus d the whole square, in which case I can therefore say that g bar is equal to g, mass of the inner earth, m bar, is nothing but rho 4 by 3 pi r minus d the whole cube upon r minus d the whole square, cancels. So in that case I will get g bar is 4 by 3 pi g rho r minus d. That is going to be the gravitation acceleration at depth d. Now let's call this as equation 2. Let's call this as equation 1. Let's divide equation 1 and 2. So if I divide equation 1 and 2, divide equation 1 and 2. So in which case I will get g bar upon g is equal to 4 by 3 pi g rho r minus d upon 4 by 3 pi g rho r, in which case I will get, this was r minus d, g bar upon g is r minus d upon r, g bar is g 1 minus d by r, right? So in that case, that is how the gravitational force varies with depth, right? Now if d becomes equal to r, that means if I move to the center of the earth, in that case g bar will be g 1 minus r upon r, g bar will be g 1 minus 1, which is 0, so g bar will be 0. So the gravitational force at the center of the earth is going to be 0, right? We will stop this here for the day. Thank you very much.